So above, we just derived our formula for calculating differentials. So dy is equal to f prime of s times dx. Notice that s, we think of that as the starting point, or starting value. And dx is equal to the change in the x value. dy is the approximate value of the change in y. That's our differential. And f prime of s times dx is how we calculate that approximate change. So let's look at an example. Let's look at an example and see how this will work with an actual function. So example 2 says the radius of a circular disk is given as 24 centimeters with a maximum error of 0.2 centimeters. So this means we think it's about 24 centimeters. It could be 0.2 more or 0.2 less. So there could be this slight change in the input of 24. And we want to get an estimate of how much the area of the disk might be changing. So first we need to know that the area of a circle is pi r squared. And this is going to be the function that we deal with, is pi r squared. And then our error, remember that's a slight change in our r value. That's the same thing as what we call dr. Right? Here it was dx, now we've got the variable r. So dr is our slight change in the r value. And in this case, that's 0.2 centimeters. And we also need a starting value. And s, we're assuming that it's about 24 centimeters. So our s value is going to be 24. When we did linearization, we would often find a p-value, and that p-value was usually the easy value to calculate. S is the same way. We're usually going to want our starting point to be an easy thing to calculate, a nice whole number. And now, what is our formula for differentials? Well, we're going to use slightly different variables here. Instead of y and x, we've got a and r. So we're going to have dA is equal to f prime of s times dr. And really, this won't be an f, that'll be an a, because we're taking the derivative of the area function. So how do we find a prime? Well, that's just taking the derivative of pi r squared with respect to r. So the pi is a constant, it just stays there. The 2 comes down, and our new exponent for r is just 1, so that just turns into 2 pi r. And we in particular don't just want the function with r, we want to actually plug in s. So this becomes 2 pi times 24 centimeters, or 48 pi centimeters. And we also need dr, we already know that, that's 0.2, so this just becomes 48 pi cm times 0.2 cm. Multiply those two together and you get 9.6 pi centimeters squared. And that is our estimate for the maximum error of the area of the disk. And then the next question is, what is the relative error and the percentage error? So to figure this out, we actually first need to know the actual area when r equals 24 centimeters. And that's a equals pi times 24 squared. That comes out to being 496 pi. And our relative error, the way we calculate that, that's equal to the error, that's a horrible way of writing error divided by the, let's say, error in area divided by the actual area. So our error was given to us by dA. Our area is A. So this is 9.6 pi divided by 496 pi. And you do that division and this comes out to being approximately 0.016 repetand. And then the percentage error, you just take relative error and you multiply it by 100%. So if we take 0.016 repetand times 100%, that comes out to being approximately 1.7%. I'm rounding up the sixes to just be a 0.17 or 0.017. So what does this mean? Why do we care about this? The idea here is that an error of 0.2 centimeters might not be that big of a deal for something 20 centimeters radius, 24 centimeters radius, but it might be a bigger deal if the radius was smaller. So how do we get a sense of how important that error is? You calculate the relative error or the percentage error. And if your percentage error is pretty small, then that means that the error isn't that important. If the percentage error here was something like 20 or 30%, that would mean that the number we're getting is pretty far off from, potentially pretty far off from the actual value. The end.